Hello everyone, welcome to practice set 6, and we're almost done, right? So if your exam is next week on the 22nd, we still have one recitation this Thursday, probably going to be about counting and the last ideas you took. Then next Monday we'll do the set 7, and I think that's it. Okay, so you're almost there, you're almost done, just a little more effort in the final sprint. And as usual, if you have any questions, let me know. Like, it might be the last chance where we officially talk is next Monday. So either this Thursday in the recitation or next Monday at this time. Just pile up the questions, okay? We can stay for as long as you want. Just make sure you have questions so I can answer them. And of course, you can always use the forum and all that stuff in the unofficial times. Okay, without further ado, let's do this. Exercise 1. Got 2 questions we want to do algorithms for. So given a list of n integers, find the average of the even integers in the list. Okay. So we talked about this. If you want to use Python or some other language, it's okay, as long as you give the details. Like if you're asked to do a sorting algorithm, you have to write it. You can't just write dot sort or whatever. Unless it's something like binary search, that might be fine. Again, if it's not asked that you write binary search, you can use it. Given a list of n integers, find the average between these evens. So you write a function or a procedure, the name of it, and what it takes as parameter. So if you want to use this function, you're going to give it a list of integers. Okay, so when you call this function, what should you give it? A list of integers. So average is 0. We started out with that. For int I is 1 up to n. So here we're assuming, okay, so you got the integers at indices 1, 2, up to n. So you're looping 1 to n over all of them. And usually how a loop works, like how we saw it in the recitation, it's okay. I is 1, for example. I is less than or equal to n. I plus plus. Or I equals I plus 1. So first of all, it's going to be A1. Then it's going to be A2, and so on. So we're incrementing by just 1 point. That's important for now. Okay, so if AI modulo 2 is 0, so now we're inside the loop. If AI modulo 2 is 0, so the remainder of division is 0 by 2, then you just add it to the average. Right now, technically it's not really average. Right now, we're just doing the sum. And at the end, we're going to divide by n, so we can get the actual average. So you can see in the solution, there's sort of spelling mistakes. You can either call this thing average, and then divide average over n. Or what would be better is to actually call this thing sum, because what we're doing currently up to here is just summing up. And eventually, when you divide by n, that's when you get the actual average. But it's just a variable name. You can call it whatever you want. So given a list of n integers, find the average of the even integers in the list. Okay, so we're actually testing if the integer itself is even. So they could all be evens. None of them could be evens. That's also possible. Okay. A different way this question might have been asked is, let's say you want to find the average of the integers at even indexes. Okay, so this part is done. That's it. If you have questions, let me know. Now I'm saying, hey, what if it was asked in a different way? What if instead of getting the average of even integers, you want to get the average of the integers at even indexes, even indices? So how would that be? That means you literally just want to sum A0, or in this case, we don't have A0. We just have A2, A4, A6, and so on. So two ways you could do this. Either the exact same function, but instead of AI, just write I. So if I modulo 2 is 0, then add it to the average. Okay, so same question, you're just checking the index is even. Or you see how here we're incrementing by 1? Because that's how usually a loop, like you're looping over the elements. So every time you increment by 1. You could, in fact, increment by 2. And you could start I by 2 as well. So I is 2, I is less than or equal to n. I equals I plus 2. So what are we looping over now, technically? We start off with A2. Next iteration, we add 2 over this, it becomes 4. Add 2, it becomes A6, and so on. So you can kind of be flexible with this depending on how the question is asked. You can initialize however you want. You can increment however you want. You could even change the condition however you want. Maybe you just want the integers at even indices that are less than n over 2. Who knows? Okay, however you want. Second question. Given a list of integers that are not necessarily distinct, may contain the same integer more than once, find the index of the first integer that is unique. Or return -1. Okay. Have a list of integers, return the first element that's been repeated. So here they're saying if the example was this, it'll be at index 6. 1, 2, 3, 4, 5, 6. 7 is the first element that's not repeated, because 9 is also not repeated. And no, the others are repeated. So 7 and 9, they're both unique, but 7 comes first. So we should include 7. If there is no unique element, you just return -1. Fair enough. Let's see how they did it. First loop is over all the elements. Okay. Then we start with the element right next to it. So if I'm gonna copy the first few elements, 1, 3, 5, 5, 3, 7, up to 7. So the first loop is gonna go over all these elements. When we enter it, we're setting j equal I plus 1. So if I was 1, meaning the index of the first element, j is gonna be 2. While j is less than or equal to n. So another sort of loop, while j is less than or equal to n, and aj is not equal to ai, increment j. Okay, increment j. And that's it. That's what this loop does. The if statement below it, it belongs to the for loop, because like they're on the same level of white spaces. Kind of like Python. So what they're saying here, okay, we keep incrementing j as an index, and we're comparing ai with aj. So 1 is being compared with 3, then 5, then 5, then 3, then 1. Once you find an element that equals it, so 2, 1, once you find an element that equals it, you'll exit the loop. Or if you have no more elements, so j becomes greater than n, that means, hey, that element should be unique. So you break. Okay, so two things will make you exit the while loop. Either you run out of elements, which should tell you that your element is unique, or you found an element that equals it, so it's known it's not unique. Finally, if j is n equals n plus over 2, n plus 1, then that means your element is unique. Because, hey, you kept going over the entire list, and you never found an element that equals it. So it's unique. You return the index of that element. Return -1 otherwise. So this return is outside the for loop. So if you did the whole for loop and you were never able to reach an element, then you return -1. There is no unique element. Okay, that's what we want to happen. That's what would ideally we'd like to happen. But while I was reading this feels wrong. Like this thing doesn't really get you the first unique element. Why? I think if we use this loop or use this procedure, it's actually gonna return this thing. So it's gonna return 5, the index of 3, instead of 6, the index of 7, which is what we want. Why does this happen? Well, okay, I is gonna be moving 1 to n. But every time we set j equals to I plus 1, so the element right next to it, and we keep looping to the end. Let me just show you what I mean. Well, assume these are, okay, so 1, that's I. We set j to equal 3. Then we keep checking. Oh, we found 1, so it's not unique. Okay, fair enough. Then we do 3. 3 is going to be I this time. J is going to be the element right next to it. So that's what we're doing. We're setting j to equal I plus 1. Okay, 3 doesn't equal 5. No. Oh, we found 3. So that's wrong. Okay, I is now 5, or pointing to the element that's 5. 5 is right next to it. It's not unique. What about this 5? There's another 5 here. It's not unique. We reached 3. So we actually reached 3. We set j to equal the element next to it. And if we keep going to the right, there is no more 3s, right? Like I is going to be now pointing to this 3. And check it, there's no more 3s to the right. So technically, j is going to equal n plus 1. We're going to return I. So this procedure, it's not really getting you the first unique element. It's getting you the first element that doesn't get repeated to the right. Okay, it's getting you the first element that's no longer repeated. So A1, A2, right now A3. I only check if on the right of A3, there's no element equal to it. But there could be an element A1 that equals it. That's what I'm trying to say. So it's not completely right. How can we fix it? Does anybody have an idea, a suggestion? So the problem is we're only comparing A3, for example. We're only comparing it with the elements on its right. That's what happens when you literally set j to equal the element on its right. We also want to compare it with all the elements before it. So hey, just set j to equals 1 every time. So j equals 1 every time. That way you're going to be comparing it with everything. So A3 is going to be compared with everything. The problem with that is it's going to be compared with everything. So it's going to be compared with itself, and definitely each element equals itself. So if we do that, it's also not going to be correct. Simply add a condition here, or j equals I. That takes care of not comparing with itself. Because aj is definitely going to equal ai when j is I. So we add an or condition. Hey, just skip that. Does anybody have a problem with this? So the solution is not 100% correct. It's only comparing elements to the right. So the way we fixed it, we're going to compare it with all the elements. So when we set j equals to 1, it's going to be compared with all the elements. Then we add this condition so it doesn't get compared with itself. Okay, let me know if that was a doozy. I did not plan on spending 15 minutes on the first exercise. This is supposed to be a short assignment. It's not going to take a lot of time with us. Exercise 2. Prove the correction of the following algorithms using induction. Okay, so they're telling us this is going to compute x power n. So again, there's a function, a procedure. You give it x, you give it n, it's going to give you x power n. Great. So what happens? We start product with 1. So this should tell you that this is going to be your final answer because of the name. We start off I with 1. Inside the loop, as long as I is less than n, we keep multiplying the product with x. So x times x times x. How many times are we doing this? Well, n times, definitely. But we want to prove that this is actually correct. So let's, using induction, let's see how they did that. Okay. So we break it off into, as we usually know, base case, inductive hypotheses, and inductive step. So the base case, what happens when n is, let's say, 0, or yeah, 0. So x power 0 is supposed to give us 1. Is that what happens here? So x is 0, it means we're never going to enter the loop. Sorry, if n is 0, we're never going to enter the loop because, hey, n is 0, we start off I with 1, the condition is wrong, we never enter the loop. But I is 1, so x power 1 minus 1, it's going to give you x power 0, it's going to give you 1. So you never enter the loop, you return 1 because that you're returning product and you never changed it. So that should be fine. Show p of 1 at first iteration, I is 1, x minus 1, you get x power 0. So they set p of 1, maybe p of 0 would be better, but I think they're assuming I is 1. Here I'm assuming n is 0. Should be same thing. Inductive step, the maintenance. Assume at the start of the ith iteration, we have this. Okay, so we have this as given. Or actually, yeah. So now we want to show that on the next step, it's also going to be this. So you have x power I minus 1 equals the product. Remember, like you're assuming this is your inductive step. We want to now show that, hey, when I increment I, it's also going to stay this. So what happens? You multiply product by x. So that should give you this, right? It's like you're multiplying on both sides by x. It becomes x power I is the product. But hey, then you increment I by 1. You're right back where you started. So this thing is different than this thing because I changed. Like for example, if here I was 5, here I is going to be 6. So here if product was x power 5, here product is going to be x power 6. Which is okay. What we care about is like the relation between the product and x power I minus 1. We care that this equals this and this equals this. This is kind of your assuming for I, the inductive step. And here you're like proving it for I plus 1. Okay, thus we maintain P of I plus 1. Okay. Finally, termination. N is something that's finite. You start I with 1. If you keep incrementing I long enough, it's gonna become greater than n, so your condition is gonna be false. When you exit the loop, you have this, you have this. So x power n equals product. Okay. Let me know if this doesn't make sense before we move on to the next one. Okay. Make sure you ask me if there's anything you don't understand. Given a list of n distinct integers, this algorithm will locate the position of the element with the largest difference with the element before it. That's a bit of a mouthful. So I think like we're taking these couples and we return the index of the biggest. So in this case, it's going to be A4 minus A3. 1, 2, 3, 4. So 9, if you subtract it with the element before it, it's going to give you 5, which is the biggest difference. So at any point, if you grab an element, you subtract it with the element behind it, and that's going to be the telltale. So obviously, you have to start I with 2. And that's going to be kind of like your base case before. You can't have a base case here if I is 1, because that's like saying you only have one element. But obviously, if you're going to do difference, you're going to need at least 2 elements. So here n is greater than or equal to 2, in other words. So start off I with 2. Then you're going to keep track of the maximum index and the max difference. So you keep track of the index such that when you subtract it with the element behind it, it gives you the maximum difference. Such a mouthful. While I is less than n, you increment I, you check if the new element, when you subtract it with the element behind it, if that's bigger than the max, you change the max and you change your maximum index. And while. That's fair enough. Finally, return I max. Whew. Let's check this. So the base case, like we said, for P of 2, assuming we're talking about the i's, is this true? Yeah. Because like we were saying, if you only have 2 elements, A1 and A2, your maximum is going to be I equals 2. Because, hey, A1, you can't subtract anything behind it. There's nothing there. So all that's left is A2. You subtract it with A1. Whatever that value is going to be, your maximum index is going to be I is 2. Because that's the only possibility. What I'm saying is, we never enter the loop for same reasons. I is 2, n is 2. So we never enter the loop. You're left with I max is 2. That's what you return here. Base case works. Hypotheses. Hypotheses. So again, it's like we're assuming for I. We want to prove now for I plus 1 below. So up to I, you have this is true. You have that the difference between this and this is the largest if you have these many elements. Remember, you're keeping track of the maximum index in I underscore max. So assume that this line is true. Now, what do we do? When we increment I by 1, this changes. This difference is no longer the maximum up to I, it's now up to I minus 1. Because here, again, same reason, I is, for example, 10. You increment I by 1, it's now 11. So only up to 11 minus 1. Up to 10, this is the largest difference. So now we check it for the next element. Is it greater than the max? If so, change the max and change the index. of the max. Here now we get the difference now takes care of all the elements up that we've reached so far. Cool. That's it. Finally, about the termination. When does this loop end? When I reaches n. Since we only enter when I is strictly less than, we're gonna stop when I is equal to n. You have this. So simply swap in this I, your n, because you have it equal to I, and you're done. That's the whole purpose of this question. You want to find I max such that the difference is the largest difference between all the elements. But again, what's largest difference is it's how they described it. You only subtract the current element with the element right behind it. Interesting question. The rest of these should be more fun, let's say. But it's not wrong to like dive deep down into this stuff, see how it's actually working. Like, why does it work? Obviously, if you run the program, it'll work. Even if you explain it, it works. But these are like the very small details that actually prove its correctness. Show this. Show the complexity of these things. Well, okay, so here we have ceiling and we have floor and ceiling. Let's see how they do this. Okay, so the floor of this and the ceiling of this, they're less than x. That's fair enough, right? So they're definitely both individually less than x. So that means you have O of x squared. Remember, O means less than. Theta means equals. And we have omega, which means greater than. So here they're trying to say prove the equal. So you have to prove omega and you have to prove O. We just did O, so it's less than or equal. Now we want to prove omega, the greater than or equal. So how we do this? Let's read it. Okay, so when we reach the third step, all we care about is that we see x squared. So that's enough, because like we don't care about the constants all that much. And we only look at the highest power in polynomials. But okay, this was okay, so -1 since we want the floor, x over 4. Okay, obviously this is going to be greater than or equal over 4. Okay, easy enough. Part 2. This is a polynomial, so that's it. When you have a polynomial, sort of like, this wasn't exactly a polynomial. Like we only care about the highest degree. Because eventually, you reach a certain point where this becomes dominant over the others. Like the others make little difference to this. So it's, in this case, this is O of x4, but here they're saying power 3. Part 3, we did that in the recitation, but in the recitation, it was 1 squared, 2 squared, all the way to n squared. And we said what they're saying. We said it's less than or equal n squared plus n squared plus n squared. But here they're saying it's less than n cubed, n cubed, n cubed. And how many of these n cubes do you have? N times. So less than n power 4, done. Put the x down, it becomes, where are you? Here. So when you put the x, this is a log, so x power something, that's something, you bring it down, it becomes x times x. Okay. So this is gonna be more powerful. Like, again, same as before, eventually this is gonna be bigger than this, because this has a highest degree, sort of. X times log s is better than just x. So yeah, it's x log x, and therefore it's O of x squared. Did they say proof it's O of x squared? Yeah. So what they did, they proved it belongs to O of x times log x. So it's obvious. So it's saying like it's less than or equal to that. So it's definitely gonna be less than or equal to x squared. Any question on this? Okay. You all must have done very well in this assignment. Exercise 4. For each of the following algorithms, what is the complexity in big O notations? We did a lot of that. So there's going to be a proof, but without even looking at it, if we want to try to predict what it's going to be, first loop is O of n. We go n times. Second loop is also O of n. Third loop is going from n to j. So going from n to j. What's the worst thing that j could be? It could be 1. So you can assume this is going to be roughly O of n. Like, it's fine if you assume that. Multiply all of these, it's going to be O of n cubed. If you actually try to prove it, you reach this. So it's not exactly n cubed, because there's going to be subtraction. Because the last loop doesn't go all the way up to n. But if n is large enough, you get this. And it's O of n cubed. The actual proof, I think you can read it on your own time. It's fine. It's just summations and multiplications. Okay. So you get that it's equal to n cubed over 2 plus n squared over 2. We don't care about the constant divisions. It's O of n cubed. Second one, it's just log n. There's a lot of explanation, but it's just log n, right? We talked about it. Start off I with n. Every time you're dividing it by 2, that's just log n. You can read the description if you want the juicy details. But like we said, if you're incrementing elements, so usually we use it to increment. If you're multiplying it by 2, or if you're multiplying it by 2, you want to reach n. Or if you start it with n, then you divide it by 2 until you reach 1. Same thing, same time. Or if you want to multiply it by 3, that's also log. It's just log base 3. And we talked that the logs are all going to be O of log n. So log base 3 of n or base 10 of n, eventually they're all equivalent. The bigger the base, it's going to be faster, but like negligibly faster when n is large enough. Algorithm 3. O of n. Every time t is I, and you divide t by 2. So the dividing by 2, this is going to be O of log n. Multiply them and log n. We got it right here. You can read these for the details. Okay. Any questions so far? 5, which is the last question. Given a list of n distinct integers, devise an algorithm that shows. Okay, devise an algorithm to print the index of all pairs having sum equals to a given input value k. This method takes a list and an integer da 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 da. Okay. So we have a bunch of elements. We just want to find the pairs that are the same. This procedure is going to be n squared. Like if you have a bunch of numbers, I don't know, they didn't, let's say they're all positive because they're integers. If you want to find the pairs such that their sum is something specific, like 9, hey, just grab one, compare it with everything else. And grab 2, compare it with this and everything else. And so on. You get its n squared. Would it be enough if we were only comparing it with the elements to the right? Like I have 1, 2, 3, and going on. I start off 1 and I keep going like this. Then for the second one, I keep going to the right. Is that enough? That could be okay. If they want like all possible pairs, like let's say here the sum is, we want the sum to be 4. So 1 and 3 are possible couples, either 1, 3 or 3, 1. So while you're going to the right, if you find 1, 3, just print 1, 3, 3, 1. So here, like what we're saying, you could start off j with I plus 1. And whenever you find it, just print ij and print ji if you want all possible couples, like both sides. But it's still gonna be n squared even if we start j with I. A little faster, but eventually it's gonna be O of n squared. So, but now for the second part, they want it even faster. Assume now that it's sorted. Modify the previous algorithm so it's faster than O of n squared. So like we said, the first thing they gave us is, okay, 1 to n, the second is 1 to n, that's n squared. Even if we modify it, I plus 1 to n, that's still gonna be n squared. So what did they do to improve it? Very nice, binary search. So what do you do? Remember, you are given k, which is the sum that you want. So remove from k ai and try to find if it exists. So in other words, let's say, okay, let's say k is 10 and a1 is 4. What the algorithm is saying, hey, remove 4 from 10 so you get 6. So the complement of a1, 4, is going to be 6. So just do binary search and try to find if 6 exists or not. If it does exist, great, you found a pair. Otherwise, a1 doesn't have a pair. That works. Only problem with it is, take this example. K is 10 and a1 is 5. And let's say that a1 is unique. If you do binary search for k minus a1, it's just going to be 10 minus 5. So 5. And remember, I said a1 is unique, so you're just going to, it's just going to give you a1. And I don't think that's what they want, right? And in this scenario, you're going to be printing a1 as a pair. That's not right. So you could still do binary search, but like add a condition that the indices have to be different, for example. So yeah, this isn't as before. This is like 99, or not, let's say 95% correct. There's this special case. What if an element is unique? If you do binary search, you're gonna get the same element. So like you're printing same pair. That's not what you want. Okay, so this is gonna be yes, n log n, because the first loop is O of n, We know binary search is log n. Multiply them, you get n log n. Okay. Before I ask you if you have any questions, I'm trying to think if we can do even something faster. Like, could we do O of n? Is that possible? Because remember, we have everything sorted. So 1, 2, 3, 4, 5. So what I'm asking is, can we do it in O of n? Might be possible. Let's check this idea. Let's say I start left, or I'm gonna have two variables, start and end. So you start at 1 at the beginning, and you have end at the, well, end. Like imagine these are indices pointing to these. If you get that a start plus a end, well, we hopefully want to print the elements that their sum is equal to k. But remember, it's sorted, let's say, in increasing order. So you have three cases. Either you get this, then great, just print. Or you get what? A start plus a end is, let's say, greater than or equal to k. If that's the case, like let's say here, k is 5. If that's the case, what you could do is just decrement end. So what happens here? We're checking 1 plus 122. 1 plus 122, that's 123. That's way bigger than 5. You have two options. Like this pair doesn't work. You can either increment start or decrement end. But if you increment start, then it's going to be now 2 plus 122, which is even bigger. So that's why you decrement end. Now end is pointing at 100. You see what I mean? We're trying. This idea is called two pointers. Let's continue with it, and we'll see if it works or not. So now end is pointing at 100. 100 plus 1, that's 101. It's still way too big for my 5. So again, I'll decrement and minus 1. Now it's pointing to 6. 6 plus 1, still way too big. Point at this. 5 plus 1, 6. So close, but not yet. We decrement, aha. We get 1 and 4, their sum is 5. So we do this. We do the printing. Well, now you can either increment or decrement. It won't matter, right? Like 1 and 4, they work. You now want to try different couples. So let's say we increment 1. Or no, I want to decrement. Let's say we decrement. So end is now pointing at 3. Remember, we just printed 1, 4 and 4, 1. So start is pointing at this, and end is pointing at this. Well, 1 plus 3, that's less than my k. So we reach the third case, which is, hey, a start plus a end is, without the equal, is strictly less than k. Then you just increment the start. We'll start plus 1. So now start points at 2. 2 plus 3, that's 5. It's equals k. So you print 2, 3, and 3, 5. Why is this O of n? Because it's simply one loop, but with 2 pointers. We'll talk in a second if it's correct or not, but this idea, it's just one loop with 2 pointers. Why 2 pointers? Well, it's, for example, how did we do it? We said, hey, start equals 1, comma, end equals n, if n is my number of elements. What's my condition? That's going to be interesting. We'll write it in a second. But my increment is just haste. Oh, and I don't even increment. That's it. Because the incrementing, it depends on this stuff. Usually at the end of the loop, you just say increment and you don't care. But no, here it matters. You'll increment if this, if this, or you'll decrement if this. It depends. So no incrementing at the end. Your condition is, hey, when should you definitely stop? Is if end is less than start. Let's say less than or equal, then you should stop. Remember, start is here and end is here. So like they're always start is less than end. If we reached, they're still less than, but they're very close. Since they're equal, remember, we said either decrement or increment, we don't care. So let's say we incremented start, it now points at this. Both start and end point at the same element. So that's it. We're no more. The elements are done. We're like they're gonna now switch sides. End is now gonna keep going here. Start is gonna go over there. It's over. The elements are done. So that's why the condition is this. That's why the condition is this. Like as long as start is less than or equal to end, then we'll keep doing it. What I wrote it in the opposite, like when we should stop. So we stop when end is now less than start, but we keep going while it's greater than start. So many words. Okay, so yeah, this is your for loop. You start with 1. You start end with n. This is your condition. Inside the loop, you write these as if statements. If the summation is equal, print. Print both ways. If it's strictly greater than, you do decrement. If it's you do this. With the print, after you do that, you either decrement or increment. Is this correct? I'm not sure. It's close, but the only thing that's bothering me is what happens when I do if they're equal. Should I increment or decrement? Right now, it feels like it wouldn't matter, but we have to think of like special cases where it might. So far, this seems good. It might work. It's like more than 80% correct. But there's that 20% of vagueness. We don't know all the special cases. Hey, maybe we can do induction to see if it works or not. But that's another idea that's sort of hinting like we can do all that. But the more important thing is the 2 pointers idea. You start with something at the start, something at the end, and one is increasing, one is decreasing, but it's just one loop. Okay. At any moment, you're either moving start or you're moving end. Yeah, that's it. It's okay. Do I have anything else to say on this? You can search the more examples on 2 pointers. Maybe it will be more clear. Does anybody have any questions while I'm thinking if there's anything I want to add? Let me know now. You're welcome. Okay, great. Okay, so if there's anything you want to take from this session, just search the idea of 2 pointers because there's really some interesting exercises on it. And if you didn't get it, really see the example so you can see why it's actually O of n. So if I'm just talking to myself, trying to make sense. If I'm saying this, I is 0. By the way, we said start and end, but it's like saying I and j. It's just a variable name. No big deal there. So you start I 0, I is less than n. If you do another loop here, j is 0, j is less than n. This isn't saying 2 pointers, this is 2 loops. Because for every value of I, you're going to be doing a lot of values for j. So I is 0, like a couple, you get j is 0, 1, 2, all to n. Then for I is 1, you get j is 0, all to n. Like that's why it's n squared, because for every I, you're doing n for j. But I itself has n values. You get n times n, that's n squared. Here, no. Like try to think of the couple idea. There's not really a couple here. Or it's possible that there's a couple, but at any moment you have start is a variable and you have end at the same time. But it's not like, hey, when start is 1, gonna be checking end for everything. No. Wish I could say it in a better way, but that's all I have right now. Again, if you have any questions, please let me know right now. Otherwise, I'll see you this Thursday. You're all very welcome. I'm gonna end the meetings, and if you have any questions, use the forum or send me a private message, whatever you want. See you next time.